So today we will continue with waves. We have already calculated the pressure term. So wave induced pressure. Now after this we will go to nonlinear waves. So this we have calculated from your linear or airy wave theory. So wave induced pressure, we have got the expression as P. So there are two components, one is minus rho g z and the other is the hydrodynamic component. So this is given by rho g a cos hyperbolic of k multiplied by d plus z and cos hyperbolic kd. Now if you want to analyze this equation of pressure, so then the first term is quite simple, that is the hydrostatic term. So this is your hydrostatic pressure. Now the one which is of interest to us, hydrostatic pressure, all of you know, that is this rho gh. The other one is the hydrodynamic component, which is the more complex part. Now this hydrodynamic component, you write this as P wave. The other part, that is the hydrostatic, we are not much bothered, but what about this? So this is equals to rho g a cos hyperbolic k multiplied by d plus z cos hyperbolic kd. Now in shallow water, or you can write like this, then the whole equation, that is the hydrodynamic component, you can write as P wave is equals to P wave with a cap, and then your sine term will come, sine omega t minus kx. Now this term, that is this P wave, becomes rho g e to the power kz, that is in deep water. So this is of interest to us, and the other in shallow water, this P wave so this will become only rho g a in shallow water. So this actually you can find out by substituting this hyperbolic equation, it is e raised to the power kz and e raised to the minus kz, you will come out like this. So these are two important inferences that we get from the hydrodynamic part. Now if you look at the diagram, then you will find that the pressure behavior is a little bit different. Say this is your surface at z equal to 0. This is z equal to 0, and we are taking the linear wave. So right now I am not going to the nonlinear wave, it's more complicated. So this is your x and z direction. So if you take a linear wave, then it will have a sine or a cosine profile. So this will come like this. Now if you want to calculate the pressure with which we are interested, because our main purpose is to calculate the force. So this is the bottom. Bottom is at z equals to minus d. Now this is important. So this one, let us take a certain at a certain position on the wave. Then your hydrostatic pressure, if you calculate, will vary linearly. So what is your hydrostatic pressure at this point? So this is your hydrostatic part, or so this is the hydrostatic component. That is that rho gz. Now on top of that, you have to superimpose this one, that is that P wave, the hydrodynamic part. So that is also varying. So you can calculate this. This is your hydrodynamic part. So this will affect your calculation for your immersed objects, especially ships. Now, there is near to the trough and near to the crest, your variation will be like this. So this is again your hydrostatic part, but the hydrodynamic component will have a variation, something like this. So this is your P wave equation. Now, there is a tendency to neglect the hydrodynamic part, since it is quite small, as you can see from this figure, but nevertheless it is important. So hydrostatic is your this one. And this is your, what is the value of P cap wave? Say at z equal to 0. So this is simply rho Ga. So that means at z equal to 0 there is a hydrodynamic component, but no hydrostatic component. In that P wave you substitute z equal to 0, you will get this. The cos hyperbolic kd, z equal to 0 will cancel it out, you are getting rho Ga. So this much is your hydrodynamic component even at z equal to 0. Now, if you take ships, sometimes when you are not very keen on this hydrodynamic component, you can take a hydrostatic part. So, for approximations, approximation at Z equal to 0, pressure can be taken only hydrostatic. But there is a big if. So, this is when this is for small, and this is called small amplitude waves. Small amplitude waves. Otherwise, you take this rho Ga, but hydrostatic pressure will be 0 at this point at Z equal to 0. Now, this is more important in case of your ships and offshore structure calculation. So, ships you will find a large part of the vessel is immersed in below Z equal to 0. So, now you have been told to calculate the pressure. So, if there is no wave, you are on the safe side, but if there is a wave, you have to take account the hydrodynamic component. So, that means there will be some pressure in this region. So, this has to be added. So, this has to be taken care of. Now, let us go to the other part, that is the nonlinear wave. Now, why we go for more complicated waves when we have the linear wave theory, which is a harmonic wave. So, these nonlinear waves, they are not harmonic, that is, they do not have the sine or cosine term. So, this is to be noted. Now, this you have to apply when waves are too steep then you should not apply your linear wave theory, or too shallow water depth. Especially near the coast, that is where you have very shallow water, then the linear wave theory is not to be applied. So, this you specially note that linear wave theory is no longer valid. So, more complicated stuff. Now, actually in the sea, sea is a very confused state of nature. Now, what you will get if you take a large number of wavelengths, you will neither get completely linear waves nor completely nonlinear waves. Say on a large scale, So, this is very interesting. On a large scale, waves linear to some extent. Linear, say you write for small number of wavelengths. For large number of wavelengths, non-linearities will be present. Now, if you draw a diagram, the picture will look like this. So, this is your airy wave or linear wave theory. So, this is fine, but after a few wavelengths you will find it is not like this. So, you will find the trough to be more flat and suddenly you will get a peak. It will come like this and then again it will go on and again you will find linear wave. So, this part you can write linear, or sometimes this is called airy wave. So, this part also is linear. That is called airy wave, but this part is non-linear. So, the diagram that we have drawn, this is called a sinusoidal wave. So, this is the actual picture in the sea. Now, if you want to, in our case, since we are ocean engineers or naval architects, we are more interested in calculating the forces, say ocean engineers more interested. We are not interested in the profile of the wave as such, but we are more interested in calculating the wave forces. Calculating the wave forces. Now, how you are getting, say, this kind of wave. So, how you are going to analyze? More interested in calculating the wave forces. Now, here actually what is done? Say each wave. So, this is one wave. So, linear wave, this is another wave and this is another wave. So, each wave has to be analyzed individually. So, this is more important, and then averaged. Or sometimes averaging is not done. You find out the maximum wave force that you are getting on the structure from the individual waves or individual wave components. So, this phenomena, that is the sinusoidal wave, they are more predominant near the coast. And the linear you get in deep water. So, you can, in the diagram itself, you can write near coast, and this is deep water. So, this is our major interest. Now, coming from the nonlinear waves, now there are various nonlinear waves. Better not to go too much deep into this. There are various types. Only two types I will tell you. Say nonlinear waves. There are two types that we will analyze. Number one is Stokes. Now, Stokes also there are various categories. So, you have second order, then you can have third order, right, and of our interest we can go up to the fifth order, where this is more complicated. So, Stokes you have these three, the other one you have sinusoidal wave. The last category you have, this is actually a variation of the sinusoidal wave, you have solitary wave. So, I will give you the diagram of this sinusoidal and solitary wave. You can see where it varies. Now, solitary wave is an extension of the sinusoidal wave with very large wavelength. There is a one single crest you will find. So, these are the three types which are very convenient, more frequently studied in the nonlinear wave category. Now, here actually what you will find, the term from where this nonlinear term has come. So, can you guess this? Now, if you want to study this nonlinearity, so then we have to go back this nonlinear term. I do not know how much of wave mechanics you have studied. Nonlinear term actually comes from the basic constitutive equations. So, that is, it is coming if you neglect the higher order terms in the equation of continuity and the momentum equation. So, this will come if higher order terms not neglected, in equation of continuity. So, all of you know what is the equation of continuity. So, from this, if you do not neglect equation of continuity and momentum balance equation. So, these are two equations, and another equation is that the boundary equation. Other equation is nonlinear Bernoulli equation. Remember, in the airy wave we have taken the Bernoulli equation to be linear. Now, if you take nonlinear Bernoulli equation, you will get an expression like this. This is del phi over del t, phi is the velocity potential. So, this will be plus half. This term you have neglected, that is del phi over del x square plus del phi over del y square plus. So, this term is the creation of your nonlinearity. Now, this is quite complex, and the last term is plus g multiplied by the surface resistance eta equals to 0. So, this you can this is your nonlinear term. Now, if you want to go get the Stokes expression, you have to substitute the values of del phi, del x, del phi, del y and del phi, del z. So, this is your nonlinear. Now, what you do, we have got the expression for the surface elevation. This expression for surface elevation is eta x t. That is, there are two terms, that is, one is the spatial and the other is the time. So, this is given as a simple cosine term. You can take sine also, but for simplicity I think let us take omega t minus k x. Now, this you can write this as epsilon eta 1 and this is x t. Now, what is this eta? This epsilon. Epsilon is equal to a multiplied by k. This is called wave steepness. Wave steepness. That is, if you take a wave like this, what is the ratio of the wave height over the length of the wave? So, this is your h and a is, of course, this is half wavelength. So, a will be like this one. So, h over a is a measure of wave steepness. Now, later on we will see that this wave steepness is a factor in deciding what is called wave breaking or white capping. So, anyway, so those are much more complex things we can discuss later on. Now, let us have a look at this Stokes theory. Now, you write your expression like this, that is the expression for, what is this expression, eta x t? This is your surface elevation. Your surface elevation equation is written in this form in terms of wave steepness. Now, if you have written epsilon as a k, then of course you have to modify your eta as eta 1 x t. So, this you can express as k to the power minus 1, k is your wave number. So, this will be cos of omega t minus k x. Now, you are getting your expression for x for eta, getting it or not? So, what is the expression for eta? So, this is simply as we have formulated before. So, this is your first term in the Stokes equation. So, this is called first order Stokes. Or sometimes you can call this as linear theory. Now, if you write the surface elevation as with second order term of epsilon, so second order you can write like this as epsilon eta 1 x t plus a higher order term, say epsilon square, and this will be eta 2 x t. So, this will give you second order Stokes. Now, the second order Stokes Actually, this equation you can obtain by you substitute eta x to the equal to epsilon x t in the Bernoulli's equation. So, your Bernoulli's equation that we have written, you substitute this and you will find an expression with the second order term. So, which one you substitute? You substitute the linear one. So, this is x t equal to epsilon. Now, Bernoulli's equation, you take the nonlinear Bernoulli's equation, not the linear one, in nonlinear Bernoulli expression. And then you simplify. So, your nonlinear Bernoulli is this del phi by del t plus half of that del phi del x term will come, and this will be del phi over del y square, and then substitute this. Plus g eta equal to 0. That means, you can see this eta term you take as this expression epsilon eta 1 x t. Now, here you substitute this, and then we have already got the expression for velocity potential that I have given you in the earlier class. So, that expression you find out the derivatives square. So, this is quite a long exercise, and after that, after doing all that, you will get an expression like this. So, eta x t will be equal to, the first term will be your linear expression a cos omega t minus k x. Now, your second term will be the quite complicated, you can work this out in your hall. So, this is cos hyperbolic k d. So, this is what you write as the second order Stokes expression. Now, from this expression you can calculate the c or wave speed. Just tell me how much is the wave speed? And so, this is called first harmonic. Why? Because it contains your cos omega t minus k x, which is a harmonic expression. Now, if you look at the second term, which is the cause of this nonlinearity, you will also find another harmonic term, that is cos twice of omega t minus k x. So, this is called second harmonic. Now, in the second harmonic, what is your c value, or this is called the phase speed. So, phase speed c is equals to, so if you look at the expression, it is that omega by k. So, here it will be twice omega divided by twice k. So, what we are seeing is this phase speed is same as the first harmonic. So, this is to be noted. So, that phase speed of second harmonic So now what will happen to this wave? Phase speed of second harmonic is same as first harmonic. Or rather you write same as phase speed. First harmonic. So now what is going to be your wave profile? Can you guess? So actually we are getting two waves, isn't it? So your surface profile will be summation of the two surface profiles. So this is called surface profile is constant. So now we are getting two waves. So just you draw the linear wave. Stokes first order. So this is your linear wave profile. Now you add the surface elevation from second order or second harmonic. So second harmonic you get a smaller wavelengths, say something like this. So I am not very good at this. Let us say now you add this and see what happens. So this is called second order Stokes correction. So actually you are getting two waves from Stokes second order theory. Now you add these two, you get the resultant wave, which will look like this. Now in this wave you will find that the trough is more flat. So this is the actual nature of your C wave, no? You will go on like this. So this is second order. So this plus this is will give you this. So this is called second order Stokes. So this Stokes theory is frequently used in offshore structure calculations, force calculations. It is simply second order. Now what you should know is where to apply this. So there is a diagram which is called the range of applicability. Now if you want to understand this diagram, before that you have to come across a number which is called a Wurzel number. This person has devised this number. So this decides on the range of applicability of various wave theories. Now here actually why this is important, later on you will find that you see your when I will talk about, there is another spectra which is called the response spectra. The spectra I will tell you in a subsequent class. You will find this response spectra is different for various structures in the ocean. Say a barge in shallow water will be excited by, now in Stokes is having Stokes second order, there are two waves. So which wave is going to excite your barge the most? Followed? And that same excitation frequency will be different, or for say a spar. You know what is a spar? A barge is having what is a shallow vessel, that is the draft is pretty small. Now this is a spar platform is having a deep draft. So which wave frequency is going to affect a barge and a spar? That will be decided by the applicability of Stokes theory. So this is where the ocean engineers have to be careful about. So response spectra different for barge and spar platform. So after studying all these wave mechanics, then actually we have to find out this response spectra. There is what will be the motion of the barge and the spar, and also the pressure terms, and which wave theories you are going to apply. So this depends on this number, which is called the Ursel number. Now Ursel number, if you write, it is given as n Ursel. So this is a ratio of steepness over relative depth cube. So this is the expression. So steepness is the wave height divided by the wavelength, and relative depth you will get by the depth of water divided by the wavelength, and simply cube this. So this reduces to h L square over d. So this is called a Ursel number. And if you want to look at the applicability diagram, you can still reduce your expression into this form. Now the velocity of propagation is nothing but L by T. C is equals to L by T, and in shallow water you will get C is equals to root over GD. So now this n Ursel you can write in this form. GHT square over D square. So that ultimately, if you substitute, you will become H over GT square divided by, now this is what you have to plot, D over GT square whole square. Are we getting it? Now in this actually L square you can write C square T square. So this becomes how much? H T square will come and C square will be GD. So ultimately you can write like that, divide both the numerator and denominator by GT square. So it's coming, expression, you substitute these two values. So now here you can plot the graph, and this graph is very important for offshore structure force calculations. Now on the horizontal axis you plot d over gt square. And on the vertical axis you plot h over gt square. Now you have to refer to this graph. So this starts from 0.00. Now there are actually 4 intervals. So this you can divide as 1, 2, 3, 4. This is 0.001. This is 0.01, 0.1. The other is 1.0. Now here also you make 4 divisions. The last one is 0.1. So your vertical axis is, your horizontal axis is actually 10 times your vertical axis. Now here you get bands. You will get a band like this. Now this region is the applicable range for your linear wave theory. So be careful, and don't apply linear wave theory in all cases. And this one you will find sinusoidal wave. And here you will find another wave which is called a solitary wave. Solitary wave is another transformation of sinusoidal wave. This is called a solitary wave. And you have number of Stokes theory. So the linear one is the first order, then you have second order. So second order will come somewhere like this. So this region is applicability of Stokes second order. So you remember like this, linear wave theory is first order, this one is second order, above that you will get Stokes third order. And this at the top you will get Stokes fifth order. fourth order is not shown. Now this region is, beyond this you write H by L, that is 0.142. This is called deep water wave breaking. So there are other things to be studied about wave breaking and white capping. This of course I will tell you not in this class, it is sufficiently advanced. What is this? What is white capping? So this is your breaking criteria, and this is deep water. The other one you will get is shallow water. Shallow water breaking. Now this happens at H by D, so this is equals to 0.78. And this line is H by H L square D cube. This value is 26. That is the Stokes limit. Beyond this you don't apply Stokes. You apply sinusoidal or solitary wave. So this is called range of applicability. So next class we will see this, the nature of this sinusoidal wave. Sinusoidal and solitary wave. Now if you want to analyze these two waves, you have to take recourse to what is called a psi. This is called a stream function. The Stokes we have solved by from the nonlinearity of the velocity potential, but we will introduce another term which is called a stream function in order to get these two wave theories. A solitary wave is actually a degenerate form of sinusoidal wave. So these waves are more present near to the shore. They affect your coastal structures. So tomorrow actually I will give you some description of offshore structures, and then we will finish this and go to wave spectra.